picture a tiny speck of dust suspended in a glass of water, right? Just jerking left, right, up, and down in pure, unpredictable chaos.
Right. Totally random.
Exactly. Now picture the prime numbers, like the unbreakable, strictly ordered building blocks of all mathematics. Today, we're going to prove to you how those two completely opposite forces are actually, well, the exact same thing.
It sounds wild, but it's true.
Welcome to the deep dive. Our mission today is to explore this incredibly dense, genuinely fascinating German manuscript titled Zeta Function, Randomness, Number Theory, Life.
Yeah, it's quite a title.
It is. Okay, let's unpack this. Because to fully grasp what this source is telling us, we have to cover a massive conceptual landscape.
Oh, absolutely. It's a huge journey.
We're going from, like, European mathematicians being literally driven to madness by the concept of infinity, to ancient Indian goddesses delivering equations in dreams, all the way to modern quantum physics and predicting high-frequency stock market crashes.
It really is an incredible journey. And to really understand how a chaotic speck of dust connects to the rigid structure of prime numbers, we have to start by setting the foundation.
Right, the historical context.
Yeah, because for centuries, mathematics essentially treated infinity as like a philosophical concept or even a theological mystery. It was just this vague, untouchable idea.
Just sort of God is infinite, that kind of thing.
Exactly.
Yeah.
It wasn't until the late 19th century that infinity was finally dragged out of the realm of philosophy and turned into an exact, rigorous science.
Which changed everything.
It did. That specific transition is what sets off the entire unbelievable chain of events we're exploring today.
Right. Because it was a brutal battle to actually define what infinity is. And that brings us to a mathematician named Georg Cantor.
Cantor is such a tragic figure in all this.
He really is.
Yeah.
So Cantor makes this shocking discovery that infinity isn't just, one big endless bucket that holds everything that never stops.
Right.
He proved that infinity actually has different levels, like different sizes.
Which at the time sounded like absolute nonsense to the mathematical establishment.
Yeah.
I mean, they hated it.
I used to think of Cantor's idea like Russian nesting dolls, but that's
Yeah.
not quite right, is it?
Not exactly, no. It's not just one sitting inside another. It's really about the scale of uncountability.
Okay, so how should we visualize it?
Well, the better way to grasp Cantor's breakthrough is to imagine trying to pair things up. Imagine you take all the whole numbers, so 1, 2, 3, going on forever, and you try to pair each one with a decimal number.
Like 1 to 0.1, 2 to 0.2, and so on.
Exactly. Cantor's diagonal argument is this brilliantly simple proof showing that even if you somehow manage to create an infinite, endless list, pairing every whole number with a decimal, you could always construct a brand new decimal that isn't anywhere on your infinite list.
Just by changing one number, right?
Right. You just change one digit diagonally down the line. And because you can always build a new decimal, Cantor proved there are vastly more decimals than whole numbers.
Wow.
Yeah. The infinity of fractions and decimals completely dwarfs the infinity of whole numbers.
But the source material highlights a really tragic human element here. Because Cantor's revelation was so radical, so profoundly destabilizing to the accepted laws of math, that his contemporaries just viciously attacked him.
They were brutal.
Yeah. Most notably, a mathematician named Leopold Kronecker led this fierce backlash, literally calling Cantor's work a disease.
Which is such a harsh thing to say to a colleague.
It's awful. Cantor saw the underlying structure of the universe, and the academic world essentially punished him for it. And the isolation completely broke him, driving him into severe psychological crises that culminated in a stay at a psychiatric clinic in Halle in 1917.
It was a devastating end for someone who reshaped our understanding of reality. And trying to clean up the exact mess that broke Cantor is what leads us to David Hilbert in the year 1900.
Right, the famous conference.
Yeah, Hilbert stands up at this massive conference in Paris and presents a list of 23 unsolved problems. He really believes solving these will finally put all of mathematics on a rock-solid, absolute, certain foundation.
No more madness, no more paradoxes.
Exactly. Specifically, his number one problem was the continuum hypothesis, which deals with Cantor's sizes of infinity. And his number 8 problem was the Riemann hypothesis, which deals with the structure of prime numbers.
Hilbert wanted math to be this perfect, impenetrable fortress.
He demanded absolute certainty. But, the universe doesn't always cooperate with our desire for perfect order.
It definitely doesn't.
Right. So in 1931, Kurt Gödel comes along, and later Paul Cohen in 1963, and they mathematically prove that Hilbert's fortress is inherently flawed.
They break the system.
Completely. They prove that within our logical systems, there are statements that are Unequivocally true, but absolutely unprovable. The system simply cannot prove its own consistency.
Wait, so Western logic just hit a massive brick wall. Like, if rigid step-by-step proofs couldn't perfectly define infinity, was there another way to look at it?
Yes, there was. But it requires moving away from the rigid sanity-breaking logic of the West and looking toward an entirely different, highly intuitive approach in the East.
Oh, this is my favorite punch of the source.
It's amazing. This is where we meet Srinivasa Ramanujan. He was an Indian mathematician who didn't operate like a Western academic at all.
Not even a little bit.
No, he was a formalist in the purest sense. For him, equations weren't just tools. They possessed an aesthetic and spiritual reality. He famously credited his profound mathematical insights to the Hindu goddess Namagiri, who he said literally wrote the equations on his tongue while he slept.
Which is just incredible. In 1913, Ramanujan writes a letter to G.H. Hardy, who is this very prestigious by-the-book mathematician at Cambridge.
The ultimate British academic.
Exactly. And this letter just casually contains 120 mathematical theorems that Hardy initially dismissed as completely wild.
He literally thought it was a prank.
Yeah, because the equations were so alien. But once Hardy realized what he was looking at, they started working together. And the precision of Ramanujan's intuition was just staggering.
A prime example from the source is the circle method they developed for the partition function.
Right, the partition function. That calculates how many ways you can add whole numbers together to make a larger number.
Which sounds simple, but...
But as the numbers get bigger, the combinations explode into the millions.
Oh, absolutely.
Ramanujan and Hardy developed a formula to calculate this, and for the number 200, their formula was only off by a tiny microscopic margin of 0.004.
It's unbelievable precision. If we connect this to the bigger picture, Ramanujan's intuitive leap wasn't just a parlor trick for number theory. He was tapping into the deep underlying structure of physical reality itself.
Which they didn't even know at the time.
They had no idea. We see this most clearly in his final days. In 1920, literally on his deathbed, Ramanujan wrote one last letter to Hardy describing what he called Mach theta functions.
And nobody understood them.
At the time, nobody had any idea what they meant. They were a total mystery.
Until decades later. I mean, in 1976, a mathematician named George Andrews is digging through the Trinity College library, and he actually finds Ramanujan's lost notebook.
Just sit in a box.
Yeah. And those exact intuitive functions, those completely mysterious Mach theta equations written by a dying man in 1920, turned out to be the exact math needed for modern physics.
Gives you chills.
It really does. The Mach theta functions are like puzzle pieces that don't quite fit standard mathematical rules, but their errors perfectly cancel each other out. And that exact balancing act is what modern physicists now use to calculate the entropy of black holes and map out quantum gravity.
It is a profound realization. Ramanujan believed that these infinite abstract number theories actually mirrored the physical universe.
And he was right.
He was. For decades, Western academics thought he was just doing abstract math. But that brings us to a monumental conceptual bridge, because in 2001, 3 modern mathematicians set out to prove exactly what physical reality the prime numbers were mirroring.
Right, they wanted to see the connection.
Exactly. They finally managed to prove how the prime numbers mathematically mimic physical randomness.
Okay, here's where it gets really interesting. In 2001, Philippe Bion, Jim Pittman, and Mark Yor published this landmark paper.
The BPY paper.
Yes, and they take these two totally separate worlds, stochastic probability, which is the math of randomness, and number theory, the math of primes, and they essentially fuse them together.
They do this by looking at something called the Brownian bridge.
Right.
To understand this, remember the dust speck we mentioned earlier floating randomly in a glass of water? That random path is Brownian motion.
Pure chaos.
Exactly. A Brownian bridge is a specific type of random path. It's a stochastic process that starts exactly at 0, wanders completely randomly for a set amount of time, but is forced to return exactly to 0 at the end.
The analogy I like to use for the Brownian bridge is imagining a dog on a really, really long leash.
That's a great way to picture it.
Yeah, so you take the dog to the park, and for an hour, that dog is wandering randomly, sniffing a tree here, chasing a squirrel there, zigzagging all over the place. That's the randomness.
The Brownian motion.
Right. But you, the owner, are holding the leash, and you force the dog to return to your exact starting point right when the hour is up. That's the bridge.
That is a perfect visualization. The path is random, but the boundaries are strictly deterministic.
Right.
Now, what Bian, Pittman, and Yor did was apply a mathematical tool called the Mellon transformation to the exact statistical probability of how far that random dog wanders, which is mathematically known as the Kuiper distribution.
Wait, hold on. You're losing me a bit.
Uh-huh.
How does tracking a random dog suddenly spit out the master code for prime numbers? Like, that feels like a massive leap. What is the Mellon transformation actually doing here?
That is a great question. Think of the Mellon transformation like a mathematical prism.
Okay, a prism.
Yeah, if you shine a beam of white light into a prism, it separates the light into its component colors,
Right.
revealing the hidden frequencies inside.
Sure.
The Mellon transform does something similar with data. It takes a probability that happens over time, like tracking how far our dog wanders minute by minute, and translates it into a frequency or geometric shape. Yeah, it reveals the hidden underlying structure of that randomness. And when Bian, Pittman, and Yor ran the Kuiper distribution through that Mellon prism, what came out the other side was the Riemann-Xi function.
Which is the exact mathematical blueprint that dictates the distribution of prime numbers.
Exactly.
That's insane. You transform the statistics of a randomly wandering dog, and you get the fundamental code of the primes.
It is wild. And the reason this profound connection exists comes down to physics, specifically the Jacobi theta function.
Which is the source talks about a lot.
Right. This function is the fundamental solution to the heat equation, which describes how heat diffuses randomly through an object. Think about how a hot radiator warms a cold room.
It spreads out.
Exactly. The heat starts concentrated and randomly diffuses outward, becoming less dense the further it spreads.
And that's exactly what prime numbers do. Like, as you go higher and higher on the number line, the prime numbers spread out and become less dense. Because Riemann's formula for the primes contains this heat equation, the physical dynamics of diffusion, like the random spread of energy, directly translates into the analytic structure of prime numbers.
The primes are quite literally distributed like cooling heat.
So if prime numbers are secretly behaving like random diffusing heat, can we use the math of probability to finally solve David Hilbert's number 8 problem, like the famous unsolved Riemann hypothesis?
That is exactly what researchers are trying to do right now. And it leads us to Xianjin Li. In 1997, Li made a massive breakthrough.
The Lie criteria.
Yes, he proved that the Riemann hypothesis is unequivocally true if and only if a specific infinite sequence of numbers, which we now call the Lie coefficients, or lambda n, are always positive.
Okay.
If even a single one of these coefficients is negative, the Riemann hypothesis is false, and our entire understanding of primes collapses.
Wow, no pressure.
Right. But because of this, mathematicians don't have to just guess at the primes anymore. They can use the exact same statistical tools an insurance company uses to predict car accidents and apply them to solve the greatest mystery in math.
And here is how the 2001 paper connects to Lie's proof. Bian, Pittman, and Yor showed that these Lie coefficients aren't just abstract numbers, they're actually cumulants of a random variable directly related to that Brownian bridge.
Precisely. And for the listener, a cumulant is just a statistical measurement that describes the shape of a data distribution.
Like how wide a curve is.
Yeah, it measures how skewed or flat a bell curve is. By proving that the Lie coefficients are cumulants of the dog's random path, we embed the prime numbers completely into probability theory.
The source gives us this incredibly fascinating visual data point about these numbers, too.
Well, the oscillations.
Yes. When you plot these Lie coefficients out, they show a smooth, upward growing trend, but riding on top of that trend are these tiny, microscopic oscillations.
Like little ripples in the data.
Exactly. But what happens if the Riemann hypothesis is actually false? What would that look like on the graph?
Well, if the Riemann hypothesis is false, those tiny oscillations wouldn't stay tiny. For very large values of n, those little ripples would violently explode.
They just shoot off the chart.
Yeah, they would grow exponentially and swing into the negative, completely breaking Lie's rule. But extensive numerical studies have been run, and so far, even at astronomically high numbers, those oscillations stay remarkably stable. They remain firmly positive, giving massive empirical support that the Riemann hypothesis is indeed true.
It's like watching a seismograph and waiting for an earthquake that never comes.
That's a brilliant way to put it.
And speaking of visualizing this data, the source material doesn't just give us equations. It provides these incredible visual mappings and IDHAH numbers that literally chart out the geometry of the infinite.
The geometric manifestations of these functions are absolutely stunning. They turn the invisible formulas into visual art.
Let's slow down and look at one of them. The rainbow torus, which is logged as ID 1463506747.
I love this one.
Me too. It visually maps the Jacobi theta function. Because the function is doubly periodic, its natural shape in complex geometry is a donut, or a torus.
Right.
And the rainbow colors wrapping around it show how the function's phase shifts and changes as it moves across the surface. But the numbers behind that ID hash are where the real magic is.
Well, the all matrix, as the source calls it.
Yes. Explain that, because it's wild.
So if you break down that ID number, 1463506747, its prime factors are 137, 163, and 65537.
Okay, so just 3 primes.
But these aren't just random primes. They are deeply fundamental constants. Take 137, for example.
Right.
In physics, this is intimately linked to the fine structure constant, which determines the strength of the electromagnetic interaction. Sir Arthur Eddington, a brilliant astrophysicist, spent his entire life trying to mathematically prove that the inverse of the fine structure constant was exactly 137.
He was literally searching for this universal underlying harmony between pure math and physics.
Exactly. He thought that number was the key.
And then you have 163, which takes us right back to Ramanujan.
It does.
Because 163 is the largest Heegner number, and Ramanujan used it to find these crazy, almost whole numbers. If you take the constant e, raise it to the power of pi times the square root of 163, you get an incredibly huge number that is almost perfectly a flat integer.
It's off by something like a quintillionth of a decimal. It's uncanny.
And finally, you have the prime factor 65537.
This one is fascinating. This is the largest known Fermat prime. And what makes this number special is a geometric property.
A polygon, right?
Right. It means a polygon with exactly 65,537 sides can be perfectly drawn using nothing but a compass and a straight edge.
That sounds impossible to draw.
Well, the source highlights a mind-boggling human anecdote here. A mathematician named Johann Gustav Hermes spent 10 entire years of his life in Göttingen, doing nothing but meticulously documenting the step-by-step instructions on how to actually draw it.
10 years.
10 years for one polygon.
Just the dedication, or like maybe the obsession, is wild. And there are other visualizations too. There are the spirals, which is ID 65537, which map the zeta function along its critical line.
They're beautiful.
Yeah, as you move up the line, it draws a spiral in the complex plane that perfectly loops through the origin at every single prime zero. And then there are the red ray structures, IDs 24257 and 28757.
The ones that use a Mobius transform.
Right. They map the prime zeros, and visually they look like a circle of incredibly dense radial pins pointing outward, just bursting into infinity.
These visuals are profound because they show us that the prime numbers aren't just a list of digits. They form a highly structured, multidimensional geometric landscape.
So what does this all mean? We've talked about mathematicians losing their minds, Indian goddesses, guys spending 10 years drawing a 65,000-sided polygon.
Right.
If you are listening to this, you might be wondering how any of this abstract infinite geometry actually affects your life today, right now in 2024 and 2025.
It's a fair question. And the applications are actually surprisingly direct and incredibly modern. Let's look at global finance.
Okay, finance.
Those exact stochastic laws from the BPY paper, the ones linking the Brownian dog to the primes, are now used to calculate spot volatility in high-frequency stock markets.
Wait, how does the roughness of primes mirror a stock market crash?
Think about what high-frequency trading is. It's millions of algorithms making rapid, seemingly random, chaotic decisions every millisecond.
That's the dust speck in the water.
Exactly. But human psychology, market rules, and algorithmic circuit breakers force strict boundaries on that chaos.
Ah, that's the leash on the dog.
You got it. Because you have chaotic decisions operating within strict boundaries, the resulting data mathematically matches the Brownian bridge, which means the stock market is moving to the geometric rhythm of the prime numbers.
That is just insane. The stock market is following prime numbers.
It is. And it extends to physics, too, specifically quantum chaos. When physicists look at the energy levels of highly chaotic quantum systems, like the atomic level of reality, they use something called Gaussian unitary ensemble, or GUE statistics.
And let me guess, it matches the primes.
It turns out the spacing between the zeros of the zeta function perfectly matches the spacing of those quantum energy levels. The primes are charting out quantum chaos.
And it's running our tech. Those fast approximation algorithms, like the Borwein algorithms used to calculate the zeta function, are actively used right now in modern cryptography to keep your digital data secure.
Yes, cybersecurity relies heavily on this.
They are also used in digital signal processing to filter out complex noise in communications. Your cell phone is literally using the geometry of infinity to send a text message,
It really is. And looking toward the future, this convergence is accelerating. We are steadily moving toward a purely probabilistic proof of the Riemann hypothesis.
which would change math forever.
Absolutely. At the same time, computer scientists are taking these exact Brownian motion models and using them in artificial intelligence. They use them to understand how information density emerges in massive neural networks.
Wow.
Furthermore, mathematicians like William Hugh Wooden are actively working on creating entirely new axioms, new foundational rules for math to go beyond what Gödel proved was unprovable, hoping to finally map the ultimate limits of the infinite.
It is genuinely staggering. Just take a second to look back at the journey we just took you on.
We covered a lot of ground.
We really did. We started with Georg Cantor losing his sanity, trying to contain the infinite sizes of numbers. We saw Srinivasa Ramanujan pulling impossibly precise equations from the divine ether.
Right.
And now we see that those exact same mathematical geometries are running global finance, securing our data, and modeling the artificial intelligence of the future.
This raises an important question,
Good.
one that gets right to the heart of what mathematics actually is.
Yeah.
The source material reveals a universe where the absolute atoms of arithmetic, the prime numbers, are dancing to the exact same physical laws as a random particle of dust floating in a liquid.
It's all connected.
It is. If our global financial markets, our quantum physics, our AI networks, and the deepest, most pristine mysteries of pure math are all governed by the exact same geometric spirals, are we simply inventing mathematics in our minds, or are we just slowly, finally discovering the underlying source code of reality itself?
Wow, that is the perfect thought to leave you with. Thank you so much for joining us on this deep dive. Keep looking at the world around you, keep questioning the geometry of the universe, and we will see you next time.